this and how to write these things up in any of these contexts. And so on the homework for Friday, I tried to give you a mixture of them, right? So you'll see some problems that are about polynomials. Then you'll see some problems that are about matrices. Then you'll see some problems that are about traditional physics vectors. These are all just some of the universes that typically show up in the theory of vector spaces. So that's for Friday. That's all we have for this week as far as the homework goes. Then next week we'll have an assignment due on Tuesday based on some of the stuff we'll mostly be covering on Thursday for this week. So anyway, but that's it for now. I did write up a pretty extensive recap of the video that you watched, the 78-minute video that I think most of you watched over the weekend. I'm going to review that right now. Then we're going to do even some more warm-up examples, which I'm going to write down here. And then we're going to do some group work where you're going to do even more practice on it. By the time we're done with today, you'll have probably seen almost 15 different examples of vector spaces and subspaces. So that's kind of what we're doing here at the start of chapter 4, right? So we've got these examples that I won't spend too much time rehashing all the way through them. Rn, right? Those are just n tuples of slots of numbers. Then you just add them slot by slot, right? Entry by entry. It's very natural. And then you do scalar multiplication by multiplying the scalar all the way through all of the slots. Yeah. And that's really just a special case of a matrix, by the way. I mean, a vector in Rn is really just like a 1 by n matrix. So you can think of it in those terms. And there's really nothing different about how the algebra works in Rn as compared to how it works in any of the matrix contexts. Notice, by the way, that our matrices, they don't even need to be a square size. Right, so we can use m by n matrices. How is it that I can get away with that? Well, it's because, guys, in a vector space, we are only doing 2 operations. I've got them up here. Addition and scalar multiplication. When a matrix it doesn't have to be a square matrix for you to be able to add the matrices together or to do scalar multiplication. It's when you want to do matrix multiplication, right? So everybody remember the dot product procedure for calculating the product of 2 matrices? You go across the rows of the first matrix and down the columns of the second matrix. Well, that is not going to work if the matrices are not square size. Here, I can't take I think I threw this at you on the exam, didn't I? A 3 by 2 matrix times itself, not possible. That's not possible because the dimensions aren't right. But here's the good news, guys. When you're talking about a vector space, you're not doing matrix multiplication. I know it sounds weird. Dr. Hammond just taught us how to multiply matrices together. And now in chapter 4, he's telling us we're not going to do that anymore. At least not for a while. The only vector space operations that we have, guys, are addition and scalar multiplication. There is no matrix multiplication mentioned there. So we're kind of ignoring something that technically we recently learned how to do. And we're just going to do just addition and scalar multiplication. Okay, anyway, so we can use matrices of any size. We can also play, as I talked about in the video, we can play with polynomials. So these are going to have a constant term. There'll be an x coefficient term all the way up to, say, x to the n. And so this is Pn of r. I do want to point out that these ai's, the a0 and the a1 and the a2, some of them or all of them could be 0. So even the top term, the a sub n, could be 0, which would mean that your polynomial actually has lower degree than n, right? If that top coefficient isn't there, or if it's 0 basically, then your polynomial stops short of going all the way to x to the n. And that's why I said here in words that we're talking about polynomials of degree less than or equal to n. Right. Less than or equal. It doesn't have to be equal to n. It could be less than that. Which is actually another reason, in order for that to be a vector space, we again have to ignore regular multiplication. Guys, if you took a quadratic, which has n equals 2, times another quadratic, which has n equals 2, what would be the power of the resulting polynomial?
4.
Quadratic times a quadratic gives you a quartic, a degree 4 polynomial. Well, that would be too high. That would not be less than or equal to 2 anymore. So it would not be in the same universe at that stage. So again, we're saved by the rules that say we're not going to do multiplication of polynomials. We're only doing addition and scalar multiplication. That's it. Nothing more than that. Right. So that's just the framework. That's the vector space framework that we're working with. Right. Okay. Then we have calculus functions. Same thing here. Of course, I can take calculus functions and multiply them together. I can take e to the x and multiply it by cosine of x, no problem. But we're not allowing that in this framework. We're only allowing ourselves to add functions together or to take a function and multiply it by a constant, a scalar. That's the rules of a vector space in terms of the operations. Okay. So these are 5 of the standard universes that we will be working with. I should point out, I should hasten to say, but it's usually not the entire universe that I care about. Right? It's usually not all calculus functions that are related to the problem that I'm working on. So let me give you an example. I'm an engineer and somebody asks me to solve this differential equation. So let me just tie this back into differential equations for a minute. There's a differential equation, right? The solutions to that differential equation, they live in this universe, the one on the bottom, the continuous functions on whatever the domain is, right? So this is the universe that my problem is a part of, but what I really care about is not the entire universe, but just those functions that solve this differential equation. That's what I'm going to be interested in. If I'm an engineer and somebody asks me to solve this differential equation, I will want to find the solutions, which will be part of this universe, but not the whole thing. And that's where the concept of a subspace comes into play. It's actually these subspaces that we are going to care about a lot more than the big universe vector spaces that I've listed on the left over there. So somebody in my first class today asked me, what's the difference between a subspace and a vector space? Which is a really good question, because when I was a student, I was so confused by that. I was like, what is the difference between a subspace and a vector space? Well, as I tried to explain in my video, I figured it out now. Took me a while, but I figured it out, so I can tell you. Really, there is no difference. It's just 2 words for the same thing. If I tell you I'm looking at a subspace, well, the fact of the matter is that's really, I think I said in my video, it's like a vector space within a larger vector space. You remember my little picture where I had S and then V like that? Right? It's a vector space within a vector space that inherits almost all of those 10 rules of a vector space from the big universe. Right? So it becomes a vector space in its own right. But the nice thing about it is that if that subset is inside of an already established vector space, like one of my universes over there, if my subspace is inside of one of those big universes, then it inherits 80% of the axioms off of this list, these 10 rules. There's only 2 others that we have to actually worry about, which are the closure under addition and the closure under scalar multiplication, which are the first 2 axioms on this handout. By the way, this is the same handout I gave you guys last week. It's also in Canvas. And the first 2 rules are the closure under addition and the closure under scalar multiplication. The rest of this list is mostly just like the algebra laws, commutativity, associativity, distributivity. Those are laws that are already true in V. They're already true in these big universes over here, and so we don't have to dwell on those. We know that those things are inherited by any subset S. The real question is just these two closure properties. This is why you saw me focusing so much in the video on that. That's why that's what we're going to be focusing on here in these warm-up problems as well. Couple of examples. Maybe we don't care about all n by n matrices. Maybe for the purposes of our application or whatever the real world problem is that we're focusing on, only symmetric matrices will really matter to us. Well, it turns out that the symmetric matrices form a subspace of all matrices, which just means that they are a vector space in and of their own right, just within themselves. If you add two symmetric matrices, you get another symmetric matrix. If you take a symmetric matrix and multiply it by a constant, you get another symmetric matrix. I wrote all of that out in the notes, right, in the video that you watched. So the symmetric matrices, they are going to be a vector space as well. And we're just calling it a subspace because it's inside of one of our bigger universes that we have established ahead of time. In a little while, guys, we're going to do some group work. And we're going to show in the group work that the skew symmetric matrices also form a subspace. And I've even got, when we do the group work, I'm going to have some hints over here that you're going to want to use. And so you can see I'm talking about, see the symmetric case in the notes, and then the skew symmetric, the definition of a skew symmetric matrix is right there. So you'll need to use that. You'll want to use that when we get into groups here in a little while. Let's see, another nice example, this is towards the end of the video, but this one is hugely important, is anytime you take the null space of any matrix, it's always a subspace. What was the null space again? The null space is just the solutions, these are the unknowns, the x vector, they are the solutions to a system of equations. But the important thing here, guys, about this system, as you can see, is that the right-hand side vector, all of the right-hand sides of all of the equations are 0. Right? So anytime you happen to notice that the S that somebody is handing you, because this is going to be on the next exam, right? I'll give you a V, I'll give you an S, and I'm going to ask you, is it a subspace of V, yes or no? That's going to be the question. If you happen to notice that S is a null space of a matrix, bingo, it's an automatic yes. It's an automatic yes because in the video, I showed that null spaces are always closed under addition and they're always closed under scalar multiplication. I showed that in the video, which means it's true once and for all. We don't have to go back. There's only one person in this room who ever has to go back and explain that again. And that'll be me 6 months from now. I'm teaching the class again for the next group. You guys already know it now that a null space of any matrix is always a subspace. And so you can just bingo say immediately that it is automatically a subspace. You don't have to reinvent the wheel. You don't have to write it out again. You just have to tell me, oh, yeah, that's a null space of a matrix. And you're good to go. Yeah, so it's actually quite nice. Let's try a few more examples, but is this okay so far? Questions here? It's just a couple of the highlights from the video, but of course there's many, many others. Let's do 4 or 5 more examples. I'm going to give you some practice with this. I'm going to give you a universe, a big V, and then within that I'm going to create a set S, and I'm going to ask you, is it a subspace of V? That's going to be the question here. So let me see if I can start off with this one, okay? So for this first one, I'm going to get my notes here. Yeah, so let's do V to be the n by n matrices. Okay, and then S is going to be the set of matrices I'll call them capital A, which belongs to V. So A is an element of V, and it's such that the determinant of A is equal to 0. And this is a yes/no question. Do these matrices that are having a determinant of 0, do they form a subspace of the n by n matrices? By the way, in the video, one of my examples in the video was I took the same vector space, and S was the set of invertible matrices. You remember that one? Well, that turned out to not be a subspace. The invertible matrices are not a subspace because they don't even have, I guess I forgot to mention this A5 axiom here, the existence of a 0 vector. If you don't have the 0 vector, obviously the 0 vector here is the all 0 matrix. If that vector is not part of S, then S has no chance of being a subspace. It's game over before you even start, right? Basically, you don't have a subspace if the 0 vector is not in the set. Now, in this case, if I change so that was in the video. The video had the invertible matrices. Is that a subspace or not? We killed that problem really fast in the video. The answer was nope, because the 0 vector, which is the all 0 matrix, is not invertible. It's not part of the set. And if you don't have the 0 vector in there, you can't have a subspace. You with me? It's just reviewing from the video. This is the opposite, though. This is saying these are the matrices that are not invertible, right? If the determinant of A equals 0, that's the matrices that are not invertible. And the question is, are those going to form a subspace? So let's think about this for a second. Usually my very first thing I like to do is just check my 0 vector. So in blue here, guys, I'm going to start writing out kind of what would be a good path forward to solve something like this. What I like to do, and probably should have put it in the recap also. This 0 vector check is kind of like the first thing I always do. I just take my 0 vector from my vector space and I ask myself, is it in S? So if I take a matrix of all zeros, what will its determinant be? 0, right? It's definitely 0. So that means that this is in S and it passes the 0 vector check. Okay, so it passes. Now, again, if this had failed, if it had failed this 0 vector check, we would be stopping right now and saying, nope, it's not a subspace. But if it passes the 0 vector check, then we actually have to go sort of back to the definition of a subspace and think about those first two axioms. The closure under addition and the closure under scalar multiplication. So that's actually what I'm going to do. Let's think about the closure under addition. Now, this takes a little bit of time and practice and experience to kind of get the hang of how to do something like this. The fact of the matter is that you need to have a gut feeling about it before you even launch into writing it down. Because if you think that it is closed under addition, then what you're going to do as a write-up will look very different than if you think, no, it's not closed under addition. So does anybody have a gut feeling? And don't be shy. It's okay. I mean, we're all friends here. We're all just trying to learn this stuff. Do you think it would be true that if you had two matrices that started off in S, in other words, if you had two matrices that both individually had determinants that were 0, does it seem like it would be reasonable that after you add those matrices together, that the determinant would still be 0? Kind of a tough one. I see some people nodding yes, some people nodding no. I will give you a hint. Did determinants play nice with addition when we were learning the properties of determinants? We didn't have a property, did we, that said that the determinant of A plus B is just the determinant of A plus the determinant of B. In fact, that was false. In fact, even in the group work, we had that show up already. So the intuition that I would have based on kind of how I've seen determinants not playing nice with addition is I would be a little bit suspect that this is not going to work. Now, if it's not going to work, and if that's actually correct, that it won't work, then what we should write down here would be an example of it, like a specific example. We can get our hands on some numbers and put them into a matrix. What size matrices do you think might be nice to work with for an example here?
2 by 2.
2 by 2, right? You don't want to get too big and messy, although you could, but it'd be nice to just keep it really, really easy. So let's just try something and just see what happens. You know, I'm gonna make 2 matrices. They're gonna be 2 by 2. By the way, there's a million right answers here. I'm just gonna write down one that would work. So I need a matrix A that has a determinant of 0. Can somebody give me one? Can somebody give me 4 numbers here to make a matrix that would have a determinant of 0? One more time. 1, 1, 0, 0. Okay, I like that. That has a determinant of 0, which means that that is in S. Okay, so we start with that guy in S. Can somebody else give me another 2 by 2 matrix that has a determinant of 0? 0, 1, 0, 1. 0, 1, 0, 1. Okay, again, AD minus BC, my little 2 by 2 determinant, that is also 0. Okay, beautiful. Now let's add them together. Let's add them together. A plus B, we're just going to slot by slot add these together. We're going to get a 1, a 2, a 0, and a 1 if I add them together. And is that still in S? If you do the determinant, A times D minus B times C, it's not equal to 0, which means that this is not in S. Look at that. We started with 2 matrices that were in S, and we added them together and got something that was not in S anymore. That means, guys, closure under addition, it fails. And one example is more than enough to show that. And so is this a subspace? It's a yes or a no. I'm going to put a big no next to that. It's not a subspace because it fails closure under addition. Do I even need to think about the scalar multiplication? Not at all. As soon as one of the conditions fails, whether it's the 0 vector check or one of these 2 closures, as soon as something fails from your list, it's game over. You can stop. You don't have to check anything else. Make sense? Okay, let's try another example. Is everybody okay with this one? It's a nice one to start off with. Let's try another. So it turns out the invertible matrices don't form a subspace, and the non-invertible matrices also do not form a subspace. Neither one of them does. Okay, so not that straightforward, I guess. Let's try another example. Let's try B to be R4. And S is going to be the set of X, comma, Y, comma, Z, comma, W. So that's a 4 tuple. It's got 4 unknowns in it, such that X plus 2Y plus 3Z plus 4W equals 0. And then I'm also going to make another equation, 5X plus 6Y plus 7Z plus 8W. That is also equal to 0. And the question here is the same one. Is that a subspace of R4? The solutions to that system there. Anybody have a comment or a thought about this particular example? Yes. Exactly. I decided to wait 5 minutes to see if I leave this for 5 minutes and do something else, and I come back to it if people are paying attention. Yes, anytime you take the null space of any matrix, it's automatically a subspace. So this is a yes, since S is equal to a null space, and it's actually a good idea to actually write the matrix down. So the coefficients of this matrix would be 1, 2, 3, and 4 on the first row, and then 5, 6, 7, and 8 on the second row. So you should tell me that matrix if you can. Now, if you didn't notice that, if you did not notice that it was a subspace, or that it was a null space, you could take the set and go through the same motions that we did over here. You could start by saying, well, is 0, 0, 0, 0 in the set? And you could just plug in 0 for all the unknowns and make sure that it works, right? And then you could check closure under addition. However, closure under addition, you're going to be taking x, y, z, w and adding that to a, b, c, d. And then when you do that slot by slot, you're going to get like x plus a, y plus b, z plus c, w plus d. And you're going to be plugging them into these equations and making sure that they still work. Does that sound like a lot of fun to do? Even for this fairly small matrix, that's going to be a pain. It's not that you can't do it. It's just, would you rather do that or would you rather just say this? I would rather just say that, right? It's so much less writing. Okay, just get that off of my screen here. So yeah, I feel like there was something else I wanted to say about this. I've lost my train of thought. Are there any questions on this? So if it's a null space of a matrix, it's an automatic yes. Yeah, it's an automatic yes. Oh, I know what I was going to say. I just remembered my thought. So on the homework for Friday, there are several questions that are asking you to find the null space of a matrix. Okay. I just want to make it clear that if I asked you to actually find the null space of this matrix, I'm really just asking you to solve this system. Solving this system is something we could have done 2 chapters ago. So on those homework problems, I think it's in 4.3 near the end of the assignment for Friday. There's 2 or 3 of these where it says, find the null space of whatever the matrix is they give you. What you have to realize is all you're doing is taking the matrix that they gave you, and you're going to augment it with zeros here, and you're going to do your EROs, you're going to circle your pivots, you're going to introduce your free variables, solve it by back substitution, all of that stuff that you trained yourself really good in chapter 2 to be able to do. Right, so this is not anything new. This is just an old problem. It's just now you've got zeros on the right-hand side of the equation. Okay, I cannot reach that. In my next life, I can erase the board. Okay, so let's see. That's a nice yes. Let's go on to another example. Everybody good? Is this good for everybody? Okay. So I've got some more examples. Let's go to number 3 here. Let's do V to be P3 of R. And then I'm going to let S, I guess I'll write it right here, be the set of P of X, which is an element of V, such that P of X is equal to AX cubed plus CX. Okay. So my big universe here are the cubic polynomials, right? P3 of R is like anything of the form AX cubed plus BX squared plus CX plus D, right? Any form of a cubic polynomial. And then within that vector space, I'm interested in only these polynomials now. These are the ones that do not have a constant term and they do not have an x squared term. They only have the top term, which is the x cubed term, and then there's some linear term, some x term. Okay. So the question is, does that form a vector space? By the way, it cannot be a null space unless it's inside of Rn. So the minute I see P3 of R here, I'm not going to use the null space reasoning for anything on this problem because it's not even in the right universe for that. But what we do need to do is go through the motions of our 0 vector check and the closure under addition and scalar multiplication. So let me start right here with the 0 vector check. Now, guys, to be able to do the 0 vector check, you have to know what the 0 vector is in the universe you're working in. So here I'm in P3 of R. So do we all know what the 0 vector is in P3 of R? In other words, which polynomial acts like 0? You add it to everything else and it just leaves it alone. I think that would just be the one that has, 0x cubed, 0x squared, 0x, and 0, all just added together. That is your 0 vector. And the question here that we need to look at is, does that 0 vector belong to S? Well, let's see, what does it take for something to be in S? For something to be in S, it has to be expressible like this. Well, I think this can be, right? Because I can just treat this as 0x cubed plus 0x. I don't have to write down the other two terms. It definitely has the form of, a coefficient times x cubed plus a coefficient times x. So this is in S. We'll check that off. That does pass the 0 vector check. The reason I do this 0 vector check is because it's so fast, and it's usually very easy to just you can almost just glance at it. Just look at what your 0 vector is and say, well, does that 0 vector, fit the requirement of the set? So you can do it very, very quickly. Of course, if it checks out like it is here, then you still have to go through the rest of verifying whether it's closed under addition and scalar multiplication. So we still have work to do here, which would be closure under addition, first of all. Start with this one. And so follow me very closely on this write-up, because this one we are going to need to write a little bit more out for. I have to take two polynomials that are in S, and they need to be kind of in arbitrary form. So what I'm going to do, guys, is I'm going to call them P of X, comma, Q of X, and I'm letting those be elements of S from the beginning. So let P of X and Q of X belong to S. Okay, so we start off with that. What I'm going to do is, if I've got two vectors that are in S to begin with, I need to add them together. But before I add them together, I need to at least somehow get them written with the notation of what S looks like. These are, after all, these are elements of S. They live in S, so they must have this format. They must have this format. Let's write that format out. So let's write P of X as AX cubed plus CX. And let's write Q of X. Now for Q, what we do have to be careful is Q is not the same as P. It's a different polynomial, so I'm not going to use an A and a C here. I'm going to pick different letters. What letters you pick, it's actually up to you. You can decide. Maybe I'll use R x cubed plus TX. So I just have to pick scalars that are maybe not the same scalars. I don't want to assume that my two polynomials were identical to begin with. Okay, but that's the way they have to look. If they are elements of S, then it means they look like that format. The coefficients could be anything, but at least the form has to look the same. The person next to you might have used, A1 and B1 and A2 and B2. That would be fine as well. So you could do subscripting and all that. It doesn't really matter what you're calling the coefficients. You just need to make sure they're very arbitrary. Okay, well then what I've got to do at the end of the day here, guys, is add these together. That's the real question for closure under addition, is when I add them together, will I get a result that is still in S? So adding these together, I'm just going to do a quick little algebra on this. So I'll add the A and the R with the x cubed term, and then I'm going to add the C and the T with the x term. I'm just adding the P of X and Q of X together and kind of grouping the terms a little bit. Looking at this, would you say that this is in S again? Let me not stand in front of it. To be in S, I have to look like this format. Something times x cubed plus something times x. What is actually called doesn't matter. So the fact that this is A plus R instead of A, no big deal. The fact that this is C plus T instead of C, no big deal. It's just some other number. The point is, this is in S. And guys, very important, I don't like to pull out my red pen, but I will on this. If you don't remember that you have to get the punchline down. The punchline is that that is an element of S again, right? It is still in S. So we have to write that down. Closure under addition is confirmed. Sweet. Okay, great. So we got that. We also need the scalar multiplication. I'll start that right here. Okay. So the way I like to do this one is I like to just say, I grab one of my vectors from before, I'll call it P of X. I'm just going to say B as above. I'm just going to kind of steal it from my first part of my calculation. I'm going to use it again. But I also need a scalar. So, and K is a real number. So that's the notation of a scalar. And what I'm going to do is do the scalar multiplication here. So I'm going to take K times P of X. And I'm going to see what I get. So that K is going to, here's the P of X. That K is just going to get multiplied through the P of X. And I'm going to end up with KAX cubed plus KCX. And what I got to do is I got to stop. I got to take a breath. I got to look at it. Say, okay, well, is that in S? Here's S. So is this something that would live inside of this S here? And as long as it has this format, the answer is yes. Would you agree that it does? I have an X cubed term. I have an X term. That's all I need. And so this is in S, and I need to emphasize that. Put my little check mark, put my element of S symbol there, and we're good to go. How could this possibly fail? This could maybe go wrong if somehow you ended up with an X squared down that you didn't have in the beginning. Or if there was a constant term that somehow showed up out of nowhere, right? It's not going to happen on this set S, but you could imagine that would be the sort of thing that would be a red flag. Something is wrong if somehow now suddenly we have X squared, or we have X to the fourth, or we have constant terms, whereas the original set never said anything about those. Right. So that would be what you'd be looking for. Is everybody with me? So this is a yes. Let's come back here. This is yes. This one works, but we had to go through the whole thing. There was no shortcut. There was no fast answer here. We actually had to verify the whole thing from beginning to end. Let me give you one more example, unless there's a question here. Again, it doesn't matter if you call it P of X. If you had called this F of X and G of X, no worries. If you had used different letters than A and C and R and T, no worries. That part doesn't really matter. Okay, let's try a fourth example. Okay, so let's take V to be P3 of R. Again, I'm going to stick with polynomials for a minute here. And I'm going to let S be the set of P of X, element, which is an element of V, and then such that P of X equals AX cubed plus 5X. So this is very similar to the one we just did. The one we just did, the polynomials had the form AX cubed plus CX. Now I've got one that has the form AX cubed plus 5X. So that's the only thing I changed. Everything else is the same. You think this one's still going to work? Why not? What could you point to that's going to go wrong right off the bat? The 5 is a problem. The 5 is a problem. In fact, your 0 vector is still the same vector here. But does the 0 vector have a 5x on it? Not at all, right? That means it's not going to have the right form to fit that form, which is what's required for something to be in S, right? So in this case, the 0 vector check fails immediately. Right from the beginning, this thing fails. The 0 vector is not in S. Be sure to put a slash through that element symbol if it does not belong to the set. There were a few, I was reading your notes, the scanned notes that you guys did for extra credit. There were a few times where people were forgetting the that little slash through this belongs to symbol. You definitely gotta have that there to make sure it makes sense. Anyway, so the zero vector check fails, so guys, it's game over. This is already a no. This is a no right from the beginning. Because one of the axioms of a vector space is that every vector space has to have a zero vector. Well, if your zero vector isn't part of your set, then I'm sorry, it's not going to have that axiom. So it's gonna be game over. It's also not gonna work to do closure under addition. Because if you have a 5x, if P of x has 5x in it and Q of x also has a 5x in it, and if you add those together, it's not 5x. 5x plus 5x is not 5x, right? 5x plus 5x is actually 10x. So it's the wrong form. So even if you sort of forgot to do the zero vector check and you start launching into the closure under addition, you're gonna run into problems. You're gonna see some problems right away. Robert, did you ever have it, Cody?
Yeah,
Please.
kind of unrelated to the actually checking about the subspace, but like,
That's okay.
is this notation rigorous enough for math usually? Like, is it okay to just assume A and C are like real numbers?
I know what you're saying, yeah. So I should probably add here that A and C are real numbers. So a stickler type of person would,
Right, and we would have to actually
I'm not
use.
trying to say you're a stickler.
No,
But you're
I'm just
absolutely right.
curious.
I should have put that there to clarify that A and C are real numbers. In this class, pretty much any scalar is always a real number scalar.
Right.
But if you look in more advanced linear algebra contexts, a lot of times the scalars could be complex numbers or other things as well. So it's a good point you're making.
Okay, so that like,
But we're kind of
Some
assuming
people
it here.
would have-
Yeah, I didn't want to
Okay.
get everybody all confused with too much notation. So I was
Yes.
just trying to keep it a little bit simple, but you're absolutely right. Okay. I would like to do one more example and then we're gonna switch gears and do group work and let you guys practice a little bit. But there's one more because I know it's on the homework. And it's one that people sometimes find a little weird. So I'd like to do it. Let me come back over here and we're gonna do a differential equation. You know, whenever I have a chance to take a linear algebra concept and see what it's going to look like in the world of differential equations, this is the class where that's gonna happen, right? That's what we're gonna wanna do. So let me do this, guys. Let's do number 5, the last example here. My vector space is gonna be sort of calculus functions that have, I'm just gonna assume the domain is like anything. So minus infinity to infinity just means I'm not really gonna limit the domain of the function at all. That's not really a big deal. But let's let S be the set of Y element of V, so Y belongs to V, such that Y double prime plus 3Y prime plus 4Y is equal to 0. I think that was the equation I wrote up here a few minutes ago. And I would like to now ask whether that forms a subspace of V or not. See, in the real world, this differential equation might be very important to you. And the big universe V isn't really, it's actually just in the background. It's not really the essence of what your problem is that you're studying. It's the differential equation that you care about. That's why I keep saying these subspaces are often more important than what's going on with the big giant universe that's kind of just in the background the whole time. Okay, so let's think about this. Zero vector check. One more time, let's do, there is one on the homework that involves a differential equation, so this would be a good one to model for that homework problem. But let's think about the zero vector check. Again, the first thing we have to figure out is, well, what is the zero vector in this universe? The zero vector, it's not the number 0, because my vector space doesn't have numbers. My vector space is functions, right? My vector space also, in this case, does not have slots. Okay, we're not working with matrices or Rn or anything like that. So my zero vector is not numbers, it's not slots. What it is, guys, if my vector space is functions, then when I say zero vector in that context, I'm talking about the zero function. Not the number zero, but the function zero. What would that look like? I could actually draw a graph of it for you. The zero vector in this universe actually looks like this. It's just a graph that is basically zero everywhere, right? This is basically y equals 0. That whole line is the zero vector in this vector space. So in blue here, I've drawn the zero vector for this particular vector space. And then the question is, does it belong to S? That's the zero vector check. We ask ourselves, is it part of S? Well, what does it mean to be part of S? It means if I take 2 derivatives of that blue line and add 3 times 1 derivative of that blue line, and then add 4 times that blue line, do I get 0? Well, the blue line is already 0. The slope of the blue line would be 0. The second derivative of the blue line would be, it's all just 0, guys. You take 5,000 derivatives of the line y equals 0, you'll get 0 every time, right? So yeah, so the zero vector check would just simply be 0 double prime plus 3 times 0 prime plus 4 times 0, and sure enough, that does equal 0, and that's a check. So that does work. That absolutely does work. Okay. So, like before, we're ready to move on to the closure under addition and the closure under scalar multiplication. Okay, so that would be the next thing I have to do. For closure under addition, I have to start off with 2 functions that are already in S. I need names for them. Now, over here in the world of polynomials, I like using P of X and Q of X. If I was working with matrices, I like using A and B. Right? You want to use notation that's kind of compatible with the universe you're in. In this case, I probably might, if I'm thinking about functions, I might call them F and G. Let F comma G be elements of S. These are the objects in this vector space, and I'm grabbing 2 of them that I'm assuming belong in S. Ultimately, I'm going to want to add them together. But you'll notice that over here, when I first wrote down P of X and Q of X, I did not add them together right away. I first stopped to say, well, what does that mean P of X looks like? And what does that mean Q of X looks like? And then I added them together on the second line down. So I'm not just going to add F and G right now, because I don't really know what to do with that. If I write F plus G on this board, I won't know what to do with that. What I really should do first is express, well, what does this mean? What I already have written down here tells me something. If F lives in S, then that means that F double prime plus 3F prime plus 4F is equal to 0. And it also means, I'm going to use a little brace here just to put the second one right with it. G double prime plus 3G prime plus 4G, that's also equal to 0. Yeah, so both F and G have to satisfy the differential equation. Okay, so now, once I kind of get that out of the way, I'm ready to add these 2 functions together. Again, I'm doing this very abstractly. I don't even know what F or G specifically is. I just know that they live in S, which means they must satisfy that differential equation. Okay, great. Well, let's take F plus G. Let's add those together. And I'm just going to stick it in on the left side here. So F plus G double prime plus 3 times F plus G prime plus 4 times F plus G. Now, it's very tempting to write equals 0 here. That's what you want. You would like to know that F plus G really does give you 0 when you plug it into the differential equation. But let's not jump to the end immediately. I have to derive that this is equal to 0. I don't just want to say, if I say equals 0 right now, I've stolen the whole thunder away from the calculation. Right? What I really need to do is just manipulate this a little bit. Does anybody have a suggestion with what I could do with the algebra of this left side that I've got so far going? Josh?
I was gonna say take out F plus G.
Like distribute it out?
Yeah.
Yeah, I mean, you can distribute it out. You've got a factor of 3 that you can multiply through, a factor of 4 that you can multiply through. Let's just like do that. It doesn't have to be anything too fancy. Let's write this as F double prime plus G double prime plus 3 times F prime plus 3 times G prime plus 4 times F plus 4 times G. That looks really good to me. So just do the algebra there. Notice that you don't have an equals 0 anywhere so far. Ultimately, I would like to get a 0 to show up on the right-hand side, but I didn't start with that. I have to actually derive that. Okay, so I'm going to be deriving that as I go along. What I have now, guys, are 6 terms. 3 of them involve F, and 3 of them involve G. And what I need to do is, well, of course, I want to use the assumptions about F and about G. So I'm going to suggest that we re-scramble the terms with all of the F terms in the front and then all of the G terms in the back, right? I've got 3 of each. I can put the F terms in the front, F double prime plus 3F prime plus 4F. I'll add a few parentheses just to really emphasize that. And I'll do the same thing in the back with the G terms. So G double prime plus 3G prime plus 4G. So this is just scrambling the terms in a different order. We're not doing anything more than that. It's just purely algebra. But the reason I did it like that, guys, is I wanted those first 3 terms to add up to 0. And I wanted those last 3 terms to add up to 0, right? Both F and G satisfied the original equation. So they would add up to 0 to begin with. And of course, now we have 0 plus 0 is equal to 0. Sorry for writing so low on my board there. I hope you can all see that, all right? So this is good news. We ended up with a 0 on the right-hand side. And that means, don't forget the punchline, guys. This is the punchline. F plus G is an element of S. And you do want to write that down. Okay. So far, so good? Let's do the scalar multiplication as well. We'll do one more practice here on that piece of it. This is where we have one vector. So we grab one vector from S, we grab a scalar, and we verify that scalar multiplication is closed. The result of the product is still in S. So let's do that. Let's let F be as above. And let's let K be any real number scalar. You notice it's just exactly the way I formatted the one earlier. This is one of those things where we're kind of getting in the habit of how you're formatting these things. It's really worth doing so that you don't have to like scramble around on each problem. And what am I supposed to write down? It almost always just starts off like this. Grab one of your vectors from above and grab your scalar K. Okay, and I'll always call it K. That's my standard choice for that. So then I'm going to look at K times F. And what am I going to do with it? I'm going to plug it in where I have the y in my differential equation. So the Kf double prime plus 3 times Kf prime plus 4 times Kf, right? That's what I'm going to start working out. And again, I'm going to resist the temptation to just put equals 0 right away. I could do that, but I'm just missing the entire point of the calculation. So instead of immediately saying that this is equal to 0, what do you think would maybe be algebraically maybe a good thing I could do with the expression I have there so far? Go ahead, Dylan.
We factor out K.
Yeah, is that what you were gonna say? Yeah, let's factor out the K, all right? I got a K everywhere in here. So I do that, I factor it out, I get F double prime plus 3F prime plus 4F. And all of that goes into those brackets. Exactly. Okay, and now the part that's in the brackets, I just kind of stare at that for a minute. F was as above, and as above means F already has this condition here, right? The F double prime plus 3F prime plus 4F, that is equal to 0. So look at that. It just becomes K times 0, which of course is 0. And so K times F is an element of S, and I put my check mark there. And guys, I have a yes on this one. Everything worked out. Everything checks out. It is closed under addition. It is closed under scalar multiplication. So this one is, yes, it is a subspace. It forms a vector space in its own right. Clear enough? So don't change anything in your notes, but I'm just going to show you how easy it is for me to change the answer from yes to no. All I have to do is maybe do that. It's still a perfectly good differential equation, but if I have a 1 on the right-hand side and I try to even do the 0 vector check, 0 plus 0 plus 0 does not equal 1. It's game over right away. It would not have worked. Yeah, so you're probably going to start noticing that the things that tend to work, the things that tend to get a thumbs up on this question will usually be equations that have 0 on one side, and also expressions that have coefficients of a flexible notation, like A and C, as opposed to A and 5, which doesn't turn out to work. So I'm just trying to give you this as a rule of thumb to kind of play with. Like I said earlier, there is no one size fits all procedure for deciding whether it's thumbs up or thumbs down just at a glance. Sometimes you just have to get in the details and write it all down to really convince yourself. So it does take some practice to kind of get good at it. So I think there were 8 examples in the video. 5 more examples here. And I have a group work that has 7 more examples, actually. Actually, when we get to the group work, the first one, we already did it. I did it as one of the warm-ups for today. So I'll leave that be. But what I'd like to do is take a 10-minute break. And during the break, I'll pass out the group work. And when we come back from the break, that's what we're going to work on next. And there'll be more practice on the same stuff. So let's go ahead and give yourself some fresh air for a few minutes if you'd like. And we'll be back in a few minutes.
Yeah. Speaking with the project that I was done, and then felt like
What?
It's not.
I gotta guess. I'm sorry, did that happen over the weekend? Was that over the weekend?
It was the morning before.
It was.
Yeah.
And I didn't even notice.
Well, I didn't have it on, yeah, my hands were broken and I was.
And you were taking an exam with a broken hand. Okay, wow. That's impressive. I assume you're right-handed.
Yes,
Okay.
luckily.
The one good miss of the whole thing.
Yeah, if I put my right hand, I probably.
You would have been having a conversation.
I don't think. You have a stigmatism? Yeah. You have golf guys. Thank you. Really?
Yeah.
This is-
I'm very blind. Blurry and then 4K.
I can see fine without my glasses. I just get a headache.
Oh, it must be nice.
So, let's go to this.
Yeah, I did stuff with my eyes. I started on paper. Look at the sun.
What?
Yeah.
The sun? Yeah. I know, Oh, snap.
There we go.
Nice.
I didn't fall off and break my arm.
That's what I'm saying. I'm like. What I'm saying. I don't know. If you raise the minimum wage and then push down. Are you still? Yeah, I feel like. Is that like bare metal? Oh, bruh. Nice, okay.
Sticker set from stickers.
Yeah.
Those so.
There's no way. No, you know what? I'm getting a neighbor fan, and so when I tried reading or tried to open the band, I mean, arrow keeping work right up to like a couple days per hour. I don't know. Did you capitalize your art? Oh, dude. Yeah.
I think it's behind.
But you did a custom marketing card. Yeah.
It's customers. Oh, I mean, I just.
The best option?
Yeah.
Kitty.
Yeah.
Dude, I took one on my VM, and God, this dude. I guess I got to finish the second part of it. We started on awesome. I want to get into that one. But so far I can file. It's
Yeah, basically, I actually do it. About the Jews.
On the last one? Yeah. Absolutely. There's some like kind of string. Rope. All real numbers are
Hey, guys, if you are ready to roll, what I'd like you to do is grab 2 or 3 people, and there are hints over here. My first class didn't seem to notice these hints. So please use them. You can skip part A, go straight into part B, and I've got a hint for you there along with what a skew-symmetric matrix is, and then some other hints on some of these other parts as well. Don't worry if you don't finish. We'll take 15 minutes and I'll let you go as far as you can through these problems. Come on up to the whiteboards. There's room in the back, on the side, and I'll come around and give you a hand and see if we can get Luis to do that too. Starting to feel a little better? Day by day. Good, good.
Yeah,
Yeah, the amount from
I just didn't think I was do the same thing again and then it's together. The one is like, what's the
You guys want to squeeze in here? Over here? Yeah, you can do that.
whatever the. So if I have 3 electrons and 9 photons.
Yeah, like.
Yeah.
It looks like.
Transposing negative A. There you go, just grab it.
He's falling over.
The other thing I would suggest you do, try to go probably without never writing down any entries.
Oh, yeah, like.
Crack level of just the definition. Just from that, so you could write 0. Zero matrix.
Yeah, right.
Don't write out. Real short. Okay. Josh, can you put a 0 next to the, sorry, can you put a minus sign next to the 0 on the right side? Yeah, right there. There you go. That's right. That's right. Try not to write out entries. Just do it very, very abstract. Like pesking around inside. That's exactly. So 0 vector, you would just write 0. Like you did, and then take the transpose of it.
Oh, yeah, symmetric is like this.
Yeah.
Negative.
No,
So we're saying that, is it valid 0?
Yeah. No, it's that's fine. We already know that A.
Just write it.
So let's go with the, you sound like you solved. You're right.
Anybody need a hand yet?
You want us to keep it abstract for the closure under addition as well?
Yes, for everything. Imagine for a second that I asked whether it's still true for 4x20. Try to make your write-up so good that it would not even matter if you see 3x3 versus 4x4 versus 5x5.
Oh.
Okay, so you don't need to write out entries, don't get into the weeds of what are actually the numbers in the. Okay. On the abstract level, kind of what I got way over there circled on the hint board. That's what I'm looking at.
I know what you mean by that. Like,
And that's the same.
Vector space.
Yeah.
Really good stuff.
Now you gotta work on data speed and transfer. It's stuff. I know, bud.
switch studies.
Anybody need help? Same thing.
Give it a 0 vector.
Here. Minus.
Which is shut off from that.
Let me just write that. Anybody else need help? No. Right. Don't forget our little. The calculations, that's absolutely correct. Oh, you did that here. Okay, perfect. Yeah, exactly. All right, great. Hey, what's up? That's what you would like to well define. So the way you're gonna write it up is you're going to fill this in. That to show how you go from right? So looking, don't even look at that yet. Just look right here, where we're starting. If I transfer A plus B. Right? That was in my video, right? Because the one I did in the video was the same thing, except it's only the same. Right? So it's just A transpose for B. Now, what do we know about A? It's negative A. And what do we know about B transpose? It's negative I. And so does that fit into this? Absolutely. Put our little check. Don't forget the punchline. The punchline you need to write down. Yeah. Therefore.
It's like,
It's gotta be in that order. The way you really do this, start from here, Get to that, then you can replace.
Okay, I don't got my binder, but.
Then you pull out.
Thank you. I need to move.
Now you got.
Yeah, I think so. Yeah.
Yes. We are.
Yeah, we're gonna do some work. Because now.
Yeah, that makes sense.
Unless
I guess it's right up.
That makes sense.
Yeah, that's fine. I think we just have to verify. I'm outside.
So the. Then. Here are
But no, you can't, you for sure can.
Yeah.
I'm not gonna.
That's like. This is, yes, yes, this is, yes. Transposing KA, you're everybody is looking at KA by deriving it, and therefore. Anybody need help? So. If you have the transpose of blob equals negative of blob, that's what it means. That's
All.
That's it, that's it.
So how does it?
Kevin, how's your group coming over here? Oh.
Yes. I'm so excited. Okay, so now we gotta figure out.
Bench. Now, just a minute. This is the major one. So far, I don't.
Oh, yeah. Oh, yeah. This is exactly.
Yeah, yeah, right. I think so.
So I'm just gonna transpose my, and I'm gonna. Go ahead and jump to the zero. So. All of this.
I don't know, I don't really get.
Yes. Anybody need a hand?
Yeah. These don't. Those are the four.
Why would you have?
So we can't use, don't get some EMS. Yeah.
It's actually gonna be.
Right.
Now we're getting. So you're like, is this? Question is. Point X want this.
Spike.
An example where. The question is, give it time. So I think an example where. After I have it.
So first, I think set up.
Same time. Oh, this is.
Oh, no, yeah.
Just like for example, five.
But we have to get it to zero. Well. Added them together.
Oh, you're under the.
So, right. You also define.
One, and -1, so that's. If you be clever about very.
As, yeah, it's not.
Something.
This one's supposed to be. Okay, this one actually. It just means you have something. Right.
Plus or minus.
It says.
You can do Yeah, how you doing, Josh? Where are we at? Did you draw the graphs?
Okay, so.
Are you guys reading my hints? RC, draw the graph. Draw the graphs. That's very important. Very important. And did you get it? That's the way we do it.
It's specifically
Yeah.
S.
Well, even this thing's up. Well, because, you know, square equals y. F over. Plus F. If you actually FOIL these out on both sides, you'll see that you get an XF here and you get a YG here. There's no. It's not the right graph. Don't have to erase it. It's good partially, but if Y squared equals X squared, claim that does not mean no Y equals that. It means that Y, right? Just roll back to. Exactly both lines. Full extent of both lines. So Y equals X, Y equals negative. Exactly. Now the question is, does that?
Yeah. Okay, yeah. Okay, so you can write it shorter.
So they're on that path. Wait, no. How do they other? The results stay on that. That's the question. Hey, guys, this graph needs a little bit.
Oh, no, no, so they're actually proposing how we go about all you guys.
It's actually equations of y plus 4 minus x. I get it. Right, you take the original size, so what your graph actually is y equals x, but also y equals negative x.
It's still making this.
Actually gives you nine. The first time I asked you. Add them together.
Right?
With the results staying in that place. That's your S. Alleged substance is an entire mix. So I'm not asking. There was one in the video that was very simple. So I actually also. Weekend, if you can find that, is that would be helpful. Otherwise, think about it from scratch.
Yeah.
And then you have to do it.
Yeah, I.
Because I think the biggest fed, like, so it's so much this, and yeah.
And if I have to go on, that's negative. I said one of those. And I remember the one. Gravel. So I can pay, there's the one, and then I can say, negative one. If I add those 2 points, so both of those are on the next. Those are in this, like, begin with, but after I add them together, I get. Is a lot messier. Okay.
Yeah, but that's. So if y, y is the right, right? Yeah, we're just trying to show the next two. This also checks out. Is that right?
Oh, you're giving me examples that do that work. And that's fine, but all I need is one example that doesn't work, that will really cinch the zero.
And that's the best.
My parabola example.
Yeah.
Just like that.
Right, okay.
Just like.
Alright, let's.
Hey, guys. Hello. I'd like to get everybody's attention because I want to introduce one more concept before we kind of run out of time today. So even if you didn't finish, just kind of a long group work. I see that most of you have gotten pretty far down, at least halfway down it. So let's go ahead and call this good for now, and we'll come back to some of these items later on, okay? So don't worry if you didn't quite finish. I have something else I want to talk about. Probably because I don't have a lot of time to do it. And I'm gonna make it work.
Yeah.
So grab my,
And then the examples.
I've got to do that too. Let's see.
Well, I don't know.
Thanks. Sorry, I've got to take that out here. Thank you. Yeah, so guys, this group work has, 7 parts to it, so I wasn't really expecting everybody to totally finish it. Some of the parts are really fast. There's a couple of them that, don't have a zero vector in them, like part F. There is the zero vector is missing. There's one of them is a null space question. I think part D is a null space of a matrix, so it's automatically yes right away. So these are, for the most part, they're pretty quick once you sort of know what you're doing. But I'll encourage you to take a look at the solutions. They are in Canvas. Group work number 6 solutions would be definitely good to work with. I want to take just 10 minutes to introduce this next section that we're going to be moving into. And this is going to be a new idea. So it's actually section 4.4, and it's called spanning sets. I want to get started on this so that when I come in on Thursday, I kind of got a foundation on this little section. Let me give you the idea here about what we're going to do next. I'm going to try to convince you that subspaces are a dime a dozen. They are everywhere within a universe feed. It is easy to make subspaces. Actually, on all of the, whatever it is, approximately 15 examples we've had so far, I've given you the vector space and then I've given you the proposed subspace S. And I've sort of asked you, is it yes or no, right? But you know what? I'm going to teach you in the next 10 minutes how to make dozens of subspaces for yourself, and that you're going to know that they're subspaces without even having to check anything. So let me get into the idea behind that. What we're going to do for this is we're going to start with a handful of vectors. let's say V1, V2, comma, up to Vn. Now, if I just start off with a handful of vectors, the chances that that handful of vectors is a subspace is slim to none. For example, if I did not grab the zero vector, if that wasn't part of my handful, then I'm missing the zero vector right away. And also, what if I grab the vector 1, 1 and I grab the vector 2, 2? Well, if I did not also grab 3, 3, it won't be closed under additions. And 4, 4, and 5, 5, and 7, 7, and 99, 99, right? You'd have to grab, if I grab the vector 1, 1, 1, 1, then I have to grab all scalar multiples of 1, 1 if I want it to be closed under scalar multiplication. That's a lot of additional vectors. Chances are not good. Chances are not good that just this handful of vectors by itself would form a subspace. But what I'm going to do is I'm going to take that handful of vectors and I am going to manually close it up under the operations. Quote unquote, close it up under addition and scalar multiplication. I'm just gonna close it. And what do I mean by I'm going to close it up? Well, what I mean is I'm gonna throw in more vectors into this handful. So if I grabbed 1, 1 and 2, 2, then I'm gonna force myself to grab 3, 3. And I'm gonna force myself to grab 99, 99. And I'm gonna throw in all the additional vectors that it would take in order to make it be closed under these two operations. Because that, after all, is what a subspace is. So there's a definition for this that we need to write down so we can start talking about this with the right vocabulary here, which is that if we are given these vectors v1, comma, v2, comma, comma, up to Vn in V. What we're going to do, guys, is we're going to form what is going to be referred to many times now as a linear combination. A linear combination, which is an expression of the form. Right, so a linear combination is an expression of the form C1 times V1 plus C2 times V2 and plus up to Cn times Vn. This is what's called a linear combination. Notice that you're only doing two operations here. You're doing some addition and you're doing some scalar multiplications. In a vector space, that's all the operations that you can do. It's all we have is addition and scalar multiplication. So I'm doing that with my handful of vectors. I'm just going to build all of these expressions. And actually, these are the expressions that we need to throw in with whatever we grabbed as our handful initially. We're going to need to close it up under the operations by throwing in all of these. Right? We're going to make every possible linear combination that we can of those vectors that we started from. And as long as we do that, we're going to have a better chance of having a subspace. Let me write down one more definition that's related to this, and then I'll state the theorem and then maybe do one quick example, which is that the set of all possible linear combinations of V1, comma, V2, comma, comma, up to Vn. If I take all of them, guys, I hope everybody understands there's billions of them. I can choose C1 to be any number. C2 can be any number. C3 can be any number. I can build those combinations all day long. All day long. So if I take all of them, right, then that set of all possible linear combinations is called the span of those vectors, and it's written this way, span, and then we use some braces here, and we list our vectors inside of that set of braces. It is the span of those vectors. So when I talk about the span of a set of vectors, I am talking about all possible linear combinations of those vectors. And here is the theorem, my friends. I just started this little section by saying I was going to give you guys a blueprint for how to make subspaces of your own free will. I'm ready to do it because it turns out, and I'm going to say this about 50 times in the next month. It turns out that anytime you take the span of anything, I don't care what it is or how many vectors it is or what they look like, anytime you take the span of anything, by the time you've collected all possible linear combinations of this set of vectors, it will always be a subspace, automatically. So the span of anything, v1, comma, v2, comma, dot, 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 up to vn, the span of anything is always, no questions asked, it is always a subspace of V. So you can make subspaces till you're blue in the face. You can grab a handful of vectors and form their span. Grab a different handful of vectors and form their span. Grab a different handful of vectors and form their span. It's very easy to make subspaces by the bazillions. By just grabbing a handful of vectors and building all possible linear combinations. Let me just give you one really simple example, and then we'll come back and do much more on this next time. Let's say that my vector space is just R2. I like to draw pictures. And I'm only going to take one vector in my hands to begin with. Let's say I take the vector 1, 2. So I like this example because I can actually draw a picture to show you what's going on. I'm going to draw my R2 vector space. It's one of our standard universes. So it's just this XY plane, and I'm just going to draw some tick marks here, set up my axes a little bit. And I'm going to grab, okay, so guys, my handful of vectors in this example is literally just one vector, which is this. So it's just, I'm going to draw it as a point right here. This is V1 right here. It's just the vector 1, 2, which we can represent as that point. So the question is, does that point by itself form a subspace? The answer is no, because we're missing the 0 vector for one thing. And so, well, we could throw that in there. But even now, this is not a subspace because I have 1, 2, but the question is, well, where is 2, 4? I should have had that. If it's going to be closed under addition, I would have to have this point as well. Oh, and then I would also have to have the negative. I'd have to have -1, -2. And I'd have to have, a tenth of whatever the vector was. And I'd have to have -1/10. And I'd have to have this point. And I'd have to have this point. And I'd have to have this point. And if I keep going like that forever, does anybody have a guess what that's going to turn into? It's a line consisting of all of the points that I'm starting to draw the dots for. Yeah, so I'm going to get this entire line. That is the span of that one single point. And so what is it? It is a line. I'll just describe it here in words for a minute. It is a line through the point 1, 2. And of course, it has to also go through 0, 0. If I tell you that I'm talking about the line that goes through 1, 2, and 0, 0, that pretty much describes this blue line. And so guys, that is a subspace of R2. If you take any 2 points on this line and you add them together, you will stay on that line, right? Or if you take any point and scalar multiply it, you'll stay on that line. And I bet you can imagine now why I'm saying that there's billions of subspaces. What if I started with the point 1, 3 instead? Well, that would just be a different line. Or the 0.5, 7. That would just be a different line. Every single line, I could draw you billions of these. You don't have to mess up your notes, but I'm just showing you like every single one. Now notice that they're all going through 0, 0. We gotta pass that 0 vector check. But other than that requirement, any one of those lines is a subspace of R2. And how do I know that? Well, it's because those lines are all simply a span of something. In this case, one single vector in R2. There's nothing that says you can only grab 1 point. Of course, we could grab 2 points, 3 points, 4 points, whatever. There's lots of other things we can do. So on Thursday, I'll get into all that and show you more about how we can make subspaces and create them. But this is at least just the start of this idea of spanning sets here. Okay, well, I am basically out of time. I have one last thing, if I could, which is I'd like to give you back your test. Not gonna go over these in class. The solution key, I've got it right here on top, actually. Solution key, I sent it out to you. It's in the resources folder. So once you grab your exam, guys, you're free to go. And I have not updated these scores into Canvas yet for the extra credit. So your scores are gonna go up once I do that. Leon, Diego.
Wait, so they have to be integers, basically, for simplicity. Obviously, we're not gonna add in my.
I awkward numbers, yeah.
Cosine.
I handle this exam.
Yeah, I feel like they have to.
I don't care. Show them.
I'm so sad. I really thought at least I got 70, but no.
I know, I thought I was like, I'm like a 60.
Yeah, I was looking at the reviews.
60. They give you also 50.
It's okay. It's okay. We can do more now. You guys already hard.
Yolanda?
But I'm not on the
Okay.
True.
That's hard to know. Yeah.
Gotta make sure that I don't get into positions where I'm underwater, drowning.
Janelle?
What's your major?
Computer and
Oh, okay.
Kathleen?
Nice. Physics.
Did you guys get the,
Robin?
get a tattoo of your major?
And Joe?
Maybe, that's what we're thinking of.
Yeah.
I'm thinking maybe getting the one that has like potential energy,
Help me out, guys.
like the triangle.
Oh.
Like it goes from like the potential to like the cube, and then I forgot what else. The V. I don't know, it's weird. Hold on, let me see if I can show you.
Arlene?
Yes, thank you. I'm so excited.
Andrew Sanchez?
Yeah, I have to. I have an exam tomorrow. Thank you.
And Alyssa?
I would get all of Newton's laws added on.
All of them?
All of
You're
them
fine.
are there.
Like just the formulas?
No, every two.
Like the
I want. the
everything
text-
at stage for rest?
I want it written in like calligraphy brown to.
Is that everybody? Anybody not get their test? Should be everybody.
If that's okay.
Yeah. No, it's fine.
Potential.
Yeah, it should be in there.
The high score was 105.
Oh my god,
Yeah.
must be nice.
There was a 105, a 104, and a 101. And a half.
Oh, I found it. It's this one.
And
Well, it's pretty hard.
it was a big, big range.
As a tramp stamp.
No, putting them both together. Yeah, I think
Like
the
this,
one
like.
in the other class, I can't remember.
I was kidding. I don't know, that'd be funny.
I can't remember which was in your section.
I'm gonna recall the formula of the American.
Yeah.
Yeah.
But there was people who did really, really well in both classes. And so that was good to see.
Do we live in a vector space?
I do. Which one do you think we live in? Huh? Trick question, right?
No.
Yeah.
Oh, R3.
R3?
That's the
Oh, yeah?
XYZ coordinate system. We live in R3.
Yeah.
I
Y'all live in R2?
Reasonable,
Okay.
interpretation.
Yeah, that's
Absolutely.
true. All right.
Yeah, good question. You're a physics person, you should like that answer.
I love questions like that.
Uh-huh, of course. Bye, guys.
Bye, everybody.
You want to help?
If you have a second, you're certainly. Certainly you can, but
Yeah, we're fine.
Racing, this is
I have a, I know you're an outdoors guy.
I am. You what?
I've voted this. So my parents, live in Utah.
Oh, Utah.
Yeah, they bought a property up in, the Wasatch.
Oh, Wasatch, yeah, uh-huh. I climbed a lot of mountains in Wasatch.
Oh, yeah.
Yeah.
I'm not good at climbing at all, but.
Oh, I'm.
Hiking and such.
Yeah.
Yeah.
That's more your-
Having like in our backyard is awesome, but,
Yeah.
yeah, they send me pictures all the time. Like you use for the property, it's fall, it's just.
Oh, yes,
It's
yes.
just- yeah.
Yeah, we don't get that in Southern California. The color changes.
Yeah.
Very nice. Yeah, that is gorgeous. Yeah, I did a hike in Utah right before I came back for the start of the semester, but it was too early
Oh.
for the color changes. So, yeah, it was, yeah, it's a really nice time of year to go hiking. I'm gonna try to go this weekend, actually, maybe to Yosemite and stuff. Although I've been reading that the federal government is maybe going to shut down. I don't know if you read about that, but that means that they won't maybe have the parks open, so I don't know what I'm gonna do this weekend. We'll see. I'll figure it out.
Good to hear.
Yeah, exactly, the usual chaos.
Well, have a good rest of the day. either way.
Thanks, Brody, you too. So I have. Please.
So with the.
Oh, okay.
I thought it
Yeah, I wanted it done before
Yeah,
class.
yeah.
So you want to know about whether you can still do it.
I will go home and do it right now.
Yep, that's fine.
Okay.
That's fine. I will be